it's a real pleasure to welcome Tim Dixon. One of the benefits of being in this business is you get to know some very, very impressive people. And if you're lucky, you get to know them over a period of time. Tim and I go back at least 32 years, perhaps more. And it's been a pleasure working with Tim. It's pretty hard to describe what Tim does beyond the general statement is that if you can do it from space-based systems observing something to do with deformation of the Earth, Tim's already done it, and he's taken a lead in it. And in most cases, he's been one of the people that really pushed the technology and got us to do it. So, with GPS and with INSAR and with all kinds of other techniques now, and almost a list of things that you could think of, earthquakes and tectonics and glacial isostatic adjustment, and now I'm sure we could think of more things trying to estimate mantle viscosity. If Tim and his coworkers have done it, Tim got his undergrad degree at Western Ontario, which I guess is now Western University, right? And then got his PhD at Scripps. Actually, he's an seagoing igneous petrologist, and then went to JPL. And I don't think he went there as a space geodesist, because I don't think space geodesy existed as an entity at the time, which Tim got in the ground floor of, and in a very short time really led the way for the development of GPS technology to measure things like the opening of the Gulf of California and study the tectonics of the Caribbean. I got involved with him in terms of studying joint studies of the New Madrid zone and later the Andes and glacial isostatic rebound all over North America, and probably a lot of other things. And Tim basically became sort of a member of the family here. My quick look is he co-advised 3 students here, Lisa Leffler, John Weber, who incidentally is Reese Elling's undergrad advisor. So Reese is a scientific grandchild of Tim's. Andy Newman, and also a postdoc, Giovanni Sella. And Tim has always been an incredibly constructive and helpful person, as well as an outstanding scientist. I could go on for this forever, but he's an AGU fellow. He's won the GSA Woolard Award. He's, that's funny. He has made enormous contributions throughout our community in all kinds of responsibilities within AGU, within GSA, within the EarthScope community. So in every ways, Tim has just been an outstanding scientist and a model geoscience community citizen. And it's a very real pleasure to welcome him, and I'm sure we'll get an absolutely superb talk. So Tim, it's all yours.
Thank you so much for that very kind introduction. I'll try to live up to it. Okay, well, the title is obvious: Improving Earthquake and Tsunami Forecasts. And I'm going to focus on subduction zones because we have a network of GPS stations on one segment of a subduction zone. So it provides some great data for us. So I'm going to be basically describing what we've learned from that data set over the last couple of decades and try to make sense of some of this complex tectonics that goes on in these subduction zones. All right, let's go to the first slide. So some of you may be familiar with this quote from G.K. Gilbert, one of my favorite geologists from the past. The people of the civilized earth, the lay clients of the seismologist, would like to know, has the time yet come for a scientific forecast of the impending tremor? So I'm pretty sure the answer is no, which is kind of embarrassing since this is more than 100 years ago. So the question obviously is, why can't we come up with reasonable forecasts for earthquakes? I mean, the atmospheric scientists do a pretty good job for hurricanes. And people want to know, how come our community isn't as good as the meteorologists? So some of you are aware of some of the great forecasting failures. The 2004 Sumatra was one event, killed about 250,000 people, mostly from the tsunami, not the earthquake itself. A few years later, similar event happened in Japan, one of the most costly natural disasters on records. A similar event is likely to hit the Pacific Northwest, places like Portland, Oregon, and Seattle, Washington, sometime in the future. So these are big events, and it's kind of our job to get our act together and figure out how to improve improve the forecasts for them. I just want to cover a couple of definitions really quickly. When I use the word forecast, and I think this is the way most people use it, it implies knowledge of the location and the size of a future earthquake, but not the timing. If you use the word prediction, it's a forecast plus a time. And there's been lots of predictions published after the fact, but they're not that useful if you think about it. So we don't think we can do it, but we ought to be able to at least to get our forecasts more accurate. And I would argue that we don't really need prediction so much as a good forecast, because with the forecast, we've got warning, maybe on a decadal timescale, time enough to harden our infrastructure in the critical areas. So let's, as a community, let's agree we need to get our forecasting act together. A few slides of review for those of you who aren't in the geophysical earthquake community. These are the subduction zones around the Pacific. We call it the Ring of Fire. They're the things that produce tends to produce the largest earthquakes and most of the really damaging tsunamis. Not all of them, but a lot of them. Here's a simple model for how these things happen. You'll hear me use these phrases: interseismic, coseismic, postseismic a lot. Interseismic, in between the earthquakes. Ocean lithosphere is subducting, it's dragging down the leading edge of the continent or whatever the other plate is. And that goes on for some period of time until the upper plate has said enough, and the stresses are too high, and I'm going to overcome the frictional barriers to motion, and you get an earthquake. And the process of that coseismic slip can wind up accelerating a large mass of ocean water, and that's what makes the tsunami. And then you get into the post-seismic phase, and it starts all over again. So I have a video of, I don't think it's going to play. Oh, yes, it will. All right, this is a short clip of a video from UNAVCO that UNAVCO put together a few years ago. It's a great tool for understanding in a qualitative way what it is we try and do with space geodesy. I'll just shut up and let you listen.
To represent the elastic nature of the overriding plate. Coastal stations are pushed northeast at a faster rate than inland stations. Although friction between the Juan de Fuca and North American plates has prevented our spring from releasing, when that friction is ultimately overcome, the resulting earthquake will cause...
Okay, I'll play that again. Notice that it's a video designed to explain the hazard in the Cascadia subduction zone in the Pacific Northwest, but it applies to most subduction zones just fine. I love the analogy with a spring. A spring shortens, it compresses during what we call the interseismic phase, and that's the strain accumulation phase. So things move inland in the direction of the subducting plate. And then when the earthquake happens, the spring springs back. And so changing in the length of the spring is a great analogy for the strain accumulation that we're attempting to measure with GPS. And as I play the video again, watch the GPS stations near the coast move inland, and then observe that the GPS stations farther inland don't move.
At each GPS station. We'll use a spring to represent the elastic nature of the overriding plate. Coastal stations are pushed northeast at a faster rate than inland stations. Although friction between the Juan de Fuca and North American plates has prevented our spring from releasing, when that friction is ultimately overcome, the resulting earthquake will cause...
Okay, good enough.
At each GPS station.
Okay, so questions. Can we use that spring analogy and basically measure a strain budget with geodesy? And if we can do that, can we use that to forecast earthquake size and location? And a related question is whether the accumulated strain gets completely released in the earthquake, or can you store some of it up over several seismic cycles, implying that after a few moderate sized earthquakes, you could have a really big one. And the third question I hope to talk a little bit about is, can we identify the shallow strain patches, the ones that are offshore, and we'll call those asperities. Those are the ones that are likely to contribute to tsunamis. If we can measure those reliably, perhaps we have a good chance of figuring out which earthquakes will make tsunamis and which ones won't. Quick review of geodesy. It's just a way of measuring displacement or strain on the Earth's surface, but we need to do it to really high precision. We're talking a few millimeters or centimeters. Basically, you can think of it as length change, just the change in length of that spring. GPS is a great way to do this, especially if we have enough money to install permanent or long-term stations fixed and able to record every day so that we can trap some of the transient events that we think are important to this process. We started doing this in the late 90s in Costa Rica. The reason for focusing on Costa Rica is that it has a peninsula that provides some land area close to the trench where all of the action is taken. Strain tends to fall off as 1/r cubed, so you want to be close to the action. It also had a history of magnitude 7.5 earthquakes and kind of a regular 50-year kind of cycle. So we thought maybe we could put our stations in there and maybe trap an earthquake. And it worked. We had an earthquake. We started installing our stations in the late 90s. By 2003, we had a pretty good permanent network of maybe 11 or 12 stations. An earthquake happened in 2012 that was more or less forecast. And so we're going to try and look at these results and see what they tell us about forecasting. Quick review of what seismic moment is. It's the energy released in the earthquake, and it's usually expressed as the product of three variables: the slip area A, and the displacement U, and then a proportionality constant mu, which many people call the rigidity. So A and U are closely related to pre-earthquake strain accumulation, and I'm going to try and convince you that they are measurable by geodesy, and that's the route, perhaps, to forecasting. Couple of more definitions. This is what I will call the canonical model for earthquakes. You've got these, instead of a nice simple 2D picture, you have patches or asperities on the subduction plate interface. Those are the things that we would like to be able to measure or map out. So those red blobs are basically related to A, the area that produces the moment. You'll see a couple of other terms on this diagram that I'm going to use. So the red stuff is the things that make earthquakes, and those are usually called unstable slip patches, or we term them velocity weakening. All that means is that once things start to move, the friction is reduced and that movement therefore accelerates. The opposite is aseismic slip or stable. What that means is that their velocity strengthening. In other words, as things start to move, friction increases, and that damps down the tendency for earthquake slip. And so in this diagram, they've labeled the up-dip part of the trench as aseismic or stable or velocity strengthening. And the thing is, if that was always true, you would never get tsunamis. So there must be some sort of change in the system. Maybe it's a state change, such that most of the time, this thing may be aseismic and stable and velocity strengthening. But sometimes something happens and it flips over into a velocity weakening state that allows tsunamis. We would love to know what that process is. And because it's offshore, we're often kind of blind to what's actually happening there. Okay, so tsunamis imply shallow coseismic slip. And one question is, do they also therefore require shallow strain accumulation? My guess is yes. And now I'm going to argue and spend the next few minutes talking to you about something called slow slip events, which I think are an important part of the story. And the reason they're important is that they release some fraction of accumulated strain. They indicate special frictional conditions, and they occur offshore, or they can occur offshore, which is where tsunamis originate. So they're going to be a part of the story. All right, so what is a slow slip event? It's kind of like an earthquake, but instead of happening over seconds or minutes, it releases its strain energy slowly over weeks or months. We can detect them with geodesy, but they also are accompanied by some very interesting seismic phenomena. People call it non-volcanic tremor or seismic tremor. low frequency earthquakes, and you'll often hear people talk about very low frequency earthquakes. In some subduction zones, possibly many, slow slip events release moment or energy equivalent to about a magnitude 7 earthquake every few years. So they're a very important part of the strain accumulation and release story. Here's what they look like in terms of geodesy and tremor. So the little black dots are daily GPS estimates of one station in Costa Rica. The red line is just a model fit to those data. And then the blue things are tremor in terms of minutes per day. So you can see that the slow slip events, which are these times when the red line moves down by about just a few millimeters, actually. The times when those slow slip events are happening is also when the time that tremor happens. And later on, I'll show a video that describes this process in a bit more detail. But the point is, we can see these things both with geodesy and with seismology. Okay, so let's talk a little bit more about strain accumulation and release. This is this process of the spring contracting during the strain accumulation phase and then abruptly lengthening during the strain release phase, the thing we call the earthquake. So we believe that strain accumulation is a necessary but not sufficient condition for large earthquakes. You also need this velocity weakening behavior. But the slow slip events imply velocity strengthening behavior. In other words, they're moving, but they don't accelerate into an earthquake, at least not most of the time. And again, that's a sort of issue we'll address later. When does can slow slip evolve into an earthquake? Some people say yes, some people say no, and I'm kind of in the middle, and I say maybe. All right, here's what a GPS station looks like. The antenna is this thing here. It's powered by solar panels here. The receiver is inside this steel box to keep the cattle and bad people away. And we've got a bunch of these now in northern Costa Rica. Here's a map of the coastal part of northern Costa Rica. You can see the Nicoya Peninsula sticking way out into the ocean. Here's the trench, the dark thing here with the white line. Northeast of it is the Caribbean plate. Southwest of it is the Cocos plate, subducting at a rate of around 7.5 or 8 centimeters per year. So it's pretty fast subduction. The Cocos plate at this point is pretty young, 25, maybe 25 million years. So it's pretty buoyant, and there's a fair amount of coupling between the upper and lower plates in this area. Okay, what does the GPS data look like in a zone like this? So it's got lots of processes embedded in this displacement history. So again, each little blue dot is a day. When you plot them on over a 10-year period like this, it all becomes a blue line. And basically, this station is moving to the northeast most of the time until there's an earthquake, and then it jumps to the southwest. And so here in this red line is the 2012 earthquake. There's a couple of other little blips. They're labeled here as SSEs. So you can see again, the slow slip events are smaller than the 2012 earthquake, but move that station in the same direction. But it moves that station in the same direction, but at a lower rate. So an earthquake looks like a vertical line on this, and it's sort of an instantaneous jump, but a slow slip event has a sloped line because it's moving to the southwest more slowly than in an earthquake. So you can imagine that the direction or the slope on this diagram is telling us about strain accumulation and release. So if things are moving up and to the right, that's strain accumulation. That's analogous to the spring shortening. And then if they're moving down, that's strain release. And they can either move down abruptly, like in an earthquake, and so the line down is vertical, or they can move down at a slope or more slowly, and that's a slow slip event. And you can see that the slow slip events are extremely regular. a little more often than every 2 years, around 21 months, I think is the repeat interval. And sometimes the slow slip events seem to indicate indicate a coming earthquake. Look at this 2012 event here. It was preceded by a slow slip event, but lots of other slow slip events have no earthquake. Another one, a smaller earthquake happened in 2017. And so the question is, and there's lots of publications in Science and Nature. It's how you get yourself published in Science and Nature these days. You find an earthquake and then you go looking for a slow slip, and a pretty good chance there was a slow slip. So then you can publish an article in Science that says the slow slip caused the earthquake, and then we can predict them, or if we could measure these slow slip events. What they don't often tell you, though, is that there's a lot of slow slip events that didn't cause earthquakes. And so there's this business of, correlation versus causality. So we'll talk a little bit more about that. Okay, so here's what the vectors look like. So on this diagram, this map, the vectors going to the upper right are velocity vectors, and they show the inner seismic strain. So basically, this is the spring shortening. The upper plate is being pushed to the northeast by the subducting Cocos plate. And then every once in a while, every 2 years, roughly, it moves the other way in these various slow slip events. And the little dark purple areas here are areas where, when we invert the displacement data from slow slip events, that's where the patches of slow slip seem to be concentrated. We can also play the game of asking, well, in between the slow slip events, it's locked. Where are those locked patches? In other words, where are the asperities that we think are future earthquake possibilities? And we get two. We get one here in the middle of the peninsula, and it turns out that that's the one that slipped in the 2012 earthquake. We get another patch here to the south and east of the main patch, and that has never had an earthquake. It always has slow slip events. So it looks as if slow slip is releasing all of the strain in this location. So that's a really interesting observation if it stands up to later data sets. These data are all taken before the 2012 earthquake. Okay, what happened in the 2012 earthquake? It was very well recorded, both by GPS, by strong motion sensors, by geodesy. This red patch is basically the thing that we believe moved during the 2012 earthquake, and it's compared to some historical estimates of where earlier earthquakes were. They're not nearly as well recorded, so their areas are not really well defined, but they roughly match that 2012 earthquake. Let's compare this red patch that slipped in 2012 with the slow slip events. We're going to invert all those slow slip vectors and say, okay, where on the plate interface was there slow slip happening? So we have a bunch of different slow slip events. They're indicated here. You can sum them up, and you get a pretty well-defined pattern of where slow slip has happened over the decade prior to the 2012 earthquake. And if we compare then those patches with the 2012 earthquake, we see an interesting pattern. Here's the earthquake here, and it's surrounded by areas of slow slip. So it's as if slow slip bound the earthquake area. And what a great way to forecast, right? You can say, okay, well, I'm going to map out the slow slip events, and where that happens, there won't be an earthquake. Well, that would be great if it's always true. The problem is, of course, we don't know if things are going to change. We do think that this lower patch, this deeper patch of slow slip down around 35, 40 kilometers depth on the plate interface, we think that that releases enough strain that you're not going to get earthquakes right in that location. But we're not sure that's true all around here. Now, that was all data before the 2012. Let's see what's changed after that big stressing event of 2012. So here is a comparison of summed slow slip prior to the earthquake So here's this deep patch of slow slip that also has strain accumulation. And here is the same patch, but based only on events after the 2012 earthquake. So there's two conclusions from this slide. One is that conditions stayed the same. The 2012 earthquake did not somehow disrupt what's happening down on the plate interface. Moreover, we can get a pretty good strain budget from this thing and claim with a pretty high degree of certainty that all of the strain that's accumulated in the interseismic phase is being released by slow slip events. Let's do the numbers. Remember I said that the subduction rate was around 7.5 or 8 centimeters a year. So 8 centimeters a year times 5 years is 40 centimeters. So each of these slides before and after the earthquake is a 5-year average. And look at the scale of slip, 450 millimeters. So roughly speaking, somewhere between 350 and 450 millimeters, or 35 to 45 centimeters, is being released in these slow slip patches. And that's pretty much what happens over 5 years of plate motion. So that's great. It says, okay, well, at least we don't have to worry about strain accumulating here. So you don't have to worry about earthquakes there. But what about all this other stuff offshore? What's happening there? Of course, we don't really know because we don't have GPS stations there, but we do have some sensitivity. We think from our coastal GPS stations, we can make inversions that make sense out to maybe 20 kilometers offshore. So let's take that data and see. Yes. Okay. So this is 1 year of data for, I think this one is the 2007. It's going to be 1 year spanning 2007. Let's just start it. And it's a mix of slow slip plus volcanic tremor. So not much is happening the first few months of 2007. Everything's staying dark blue. And now you can start to see a few patches turning brighter. There's some tremor starting. There's a big patch offshore slipping. And then there's the down dip patch slipping, roughly coincident with the tremor. Okay, now let's take a look at compare pre and post. I want to look first of all at strain accumulation. Now I got to back up a little bit and admit that when we do these inversions, there's a little bit of funny business going on because we have to guesstimate an amount of dampening that the inversion is forced to be constrained with. And we can either be loose on the damping and get very detailed in pictures of what's happening on the plate interface, but it's probably an artifact. Or we can be very tight on the damping and force a very smooth kind of solution. So what we've done here is bracketed those two ways of damping these inversions. So the bottom one is very tightly constrained, such that all of the slip is just forced to be on one slip patch. And then on the upper panels, we've allowed it to have a little more spatial variation. And the truth is probably somewhere in between, right? But what's interesting is that regardless of which damping solution we pick, the white line, the white contour indicates the 2012 slip patch. And we get some really good agreement between the 2012 slip rupture zone and what we're inferring to be locked. Take a look up at this pre-earthquake and post-earthquake upper two panels. There's a pretty good agreement between these patches of slip that ruptured and patches of slip that are locked before the earthquake. And notice that in both cases, regardless of damping, the picture is pretty much the same pre and post-earthquake. And that tells us something very important. There are previous publications that suggested that things like locking patterns and slow slip occurrence are sensitive to stress conditions. But an earthquake generates a lot of stress, and the similarity of the pre and post earthquake patterns of strain accumulation and slow slip, strain release, suggests that these patterns are not strongly influenced by stress change. So to me, that implies that the spatial control of these processes has to be long-lived. It has to survive through an earthquake. Obviously, to me at least, it's reflective of the geological conditions on the plate interface. So that's kind of an encouraging sign. It says that if we start to make these observations in a routine way, they're going to tell us something long-lived. It's not going to change with the next earthquake. Okay, now I want to go back to this business of, can slow slip events be used to predict earthquakes? There is a hypothesis in the literature called the accelerating moment release, or AMR hypothesis. These studies assert that earthquakes are preceded by foreshocks or possibly slow slip events that increase in moment or energy release right up to the time of the earthquake. So if that's correct, we should see slow slip leading to the earthquake. And remember, I did show you some GPS displacement patterns that suggest that a couple of earthquakes do have slow slip events just before the earthquake. So maybe we can test this hypothesis out. We're going to look at this 2012 one, beautiful SSE starting about 6 months before the earthquake. So we want to look and see right near the earthquake, what's happening. Well, it turns out that there is some acceleration of slip prior to the earthquake, up to a few millimeters per day, but it doesn't clearly show accelerating right up to the moment of the earthquake. And there's a rough coincidence of the slow slip moment with aftershocks. So let's see, the number of aftershocks are these gray bars, and this blue line is the peak slip rate that we get from GPS. And so the peak in aftershocks and the peak slip rate actually happens about 10 days prior to the Costa Rica earthquake. It turns out there was another earthquake in El Salvador much farther away. I don't think that's related, but we plotted on there just to be honest. So I don't think this is clear one way or the other, but to me, it's not a slam dunk for the accelerating moment rate hypothesis. I would have loved to see these things accelerate right up to the day of the earthquake. Then I might be convinced. With this pattern, it's a maybe. All right. Let's look at another example. We've got one in 2017, a smaller earthquake. It happened to the southwest of our network, but we had a few stations that recorded it. So here's a slow slip event. It's pretty much right on schedule. There was one 2 years before, there was one 2 years after, this one happened, and an earthquake happened. So the question is, did it cause the earthquake, or could we use this kind of phenomena to predict or forecast these things? So here's another movie. Let's see if we can get this to play, that shows this event in a little more detail. It's going to start in May of 2017, and then the earthquake will be happening in November. So we got about 6 months of slow slip prior to this earthquake. And if you watch these columns over on the right, you'll see a little cursor move through showing where you are in the displacement data. So it starts with an event offshore, which is kind of interesting. Then there's little events all over the place. Now it's July. There's the red thing is the slow slip and the earthquake. I'll play it once more. Now we're into 2018. Slow slip is still going on, and then it kind of dies away. All right, let's play it once more. Here's May, June, July, August, September, October. There's our earthquake. December, next year, January, February, March. So there are stations close to the earthquake that appear to have slipped just prior to the earthquake. But in fact, the earthquake started 6 months earlier. And the problem, of course, is that you don't know if, well, let's go back. They happen every 2 years. If an event is 6 months, that means 25% of the time we have an earthquake happening. So it's not a super diagnostic event. On the other hand, there's tantalizing evidence that the slow slip propagated towards this earthquake. So I think the jury is out. Here's a map of when these stations started. Here's that 2017 earthquake. There's slip patch has been estimated 2 ways. Here's our solution. This is a solution from the Costa Rica group. But notice that these ones started in May and June. These ones are happening back later on in October. So there's a hint that this thing is propagating towards the earthquake. Whether we can say it caused the earthquake, I don't know. Maybe it's just like, I remember a few years ago, people used to write papers about tides causing earthquakes, or you'd get more earthquakes at high tide or low tide. And I think basically people wind up concluding, well, the earthquake's going to happen anyway. The tide might be added stress just a little bit and kick the event into happening, but it's not a diagnostic tool. It may be that we'll wind up viewing these slow slip events the same way. I should point out that we've calculated things like Moore Coulomb failure stress. It's just negligible at the location of the earthquake. So again, I'm just not sure it's going to wind up being a useful forecasting tool. Okay, let's go back and talk about tsunamis. They're offshore, implying that we need to do a better job of monitoring what's happening. So there's 2 ways we can think about improving our data offshore. The best way, in my opinion, would be seafloor geodesy, and I'll talk a little bit about that. But since we don't have it right now, we could also augment our simple kinematic locking models and add a little physics. And that's what I want to show next, because we can do that today. So the idea is, if you push on one end of the table, the other end is going to likely move unless the middle of the table is really squishy, right? And the same thing probably happens in subduction zones. If you have a locked patch that's imposing a stress on the overlying plate, there's a stress shadow that propagates some distance uphill, so to speak. And the amount depends on the rheology of the upper plate. So we're going to use that simple model to try and guesstimate what's happening offshore. It turns out, as with any model, you got to make some assumptions. Here's a model where the assumptions tend to maximize the offshore locking. And if we do that, we got a lot of locking offshore. What's more interesting is that if we use a model that minimizes the amount of offshore locking, we still get a locked patch offshore. So that, to me, is really important. We can't measure this directly yet, but based on what we know about from the GPS data and our knowledge of the rheology of the way the Earth works, it looks like there's locking happening offshore, which implies that we are at risk of tsunamis in this area, even though there's no historical record. This is the same data now, just plotted. I've done a profile starting at the trench and going north to the northeast in the direction of plate motion. So the blue line is the minimum coupling model, and the orange line is the maximum coupling model. And they show that somewhere between 0.6 and 0.9 is the coupling ratio, where 1 would be totally coupled. One interesting thing is that minimum and maximum model define peak slip onshore, which brackets the co-seismic slip pattern observed in the 2012 earthquake. That's this purple line that's, where did my cursor go? Here. Here's the 2012 earthquake. Here's peak slip right in between the maximum predicted by Model A and Model B. Now you can ask, okay, what is slow slip doing? Well, slow slip is not releasing, as best we can tell, is not releasing all that accumulated strain. And you also cannot get rid of it with afterslip. We did a pretty good job of measuring afterslip in the 2012 earthquake, and that's the green line here labeled post-seismic slip. It doesn't release hardly anything offshore as best we can tell. So the implication is that the stress shadow model indicates slip deficit accumulating offshore. It's not released in the 2012 earthquake. It's not released in afterslip. So we think it's evidence for long-term strain accumulation. Notice that long-term here is about at least 170 years because we've had 4 earthquakes starting in the mid-1800s. So I don't know if you can hold on to strain through 4 earthquakes, but things like the Tohoku earthquake in Japan suggest that is certainly possible. Okay, seafloor geodesy. What are the goals for seafloor geodesy, or what are the options? So I'd like to point out something that is not widely appreciated. Most seafloor geodesy efforts focus on how do we go out to the deep ocean, 3, 4, 5 kilometers, and do our job. But in subduction zones, there is a lot of real estate that is in quite shallow water. So here's 3 subduction zones, my favorite in Central America, everybody else's favorite in the Pacific Northwest, and then the area around New Zealand. And the red stuff is everything that's under 200 meters of water depth. So at least for this part of Central America, here's the trench here, and this deep, dark purple line. Something like 50% of the real estate between the coastline and the trench is under 200 meters. So I think we could be clever about seafloor geodesy and design some stuff that would get us measurements and data in that part of the subduction zone. Wouldn't work everywhere, but it'll work in some places. So here's my favorite technique for doing that. It's basically brute force GPS. I'm just going to make a big long pole, stick it on a concrete anchor, and put a GPS on top and see what happens. So astoundingly enough, NSF funded us to do this. And we actually built the thing and we deployed it off of Tampa Bay. Here's a picture of it just after it was put in. Here's a drone shot of it. Here's the barge that launched it. Here's where the GPS antenna goes. And there's a float that keeps it vertical. You can just see it under the water here. And here's the big thing that's anchored to it. We just put this huge concrete block on the bottom of it and drop the whole thing in the water. So it's pretty cheap to build. There's nothing too high tech. The expensive part, like most marine things, is deploying it. So we did it on the cheap and didn't put it very far out because we didn't want to pay for the ship to go too far. So we put it in probably like the worst place in the world, a tidal channel where the water flushes in and out of Tampa Bay every day. So this thing deflects by very large amounts. But so the trick here is, you've got GPS, so you can measure where it is. And if you're a geodesist, you can also measure things like tilt. So we put tilt meters on this pole and use the tilt data to correct for the thing as it wiggled back and forth with the tide. So here's raw data from just 24 hours. The time scale is up here. And look at how much this thing moves. I mean, it's a huge amount. It moves like plus or minus 3 meters, both east and north. It's rocking back and forth by a huge amount. But we can use the tilt meter to correct. And so here is, if you do the tilt corrections, you get a little nice tight circle. And if you add it up here or expand the view, now you've got your positions to a few centimeters. So this is basically how we do it. So what's the data look like? Well, first of all, does the thing last? So we have this interesting phenomena in Florida called hurricanes. And shortly after we put the thing in, it got hit by a hurricane. It got hit by Hurricane Michael. It wound up dragging the anchor of half a meter or so during Hurricane Michael. And the following year, it got hit by an even bigger storm that didn't make the national news, so they didn't put a name on it, but it also moved during that storm. But the thing survived just fine. And in between these hurricanes, you can kind of get an estimate of how this thing performs. So here's a 5-month period in 2019 in between all the storms and hurricanes. And the RMS scatter about this thing is maybe 10 a centimeter, 10 millimeters in the horizontal, in the 10 a centimeter in north and up, and 2 centimeters in the east. So that's pretty good. So we argue that this is not a bad way to do offshore geodesy, at least in shallow water. Here's a map of where you could potentially put these things. So here are places with the distant. I'll focus here on Nicaragua. Let's see, where's my cursor? So these are distances where you can be either 40 meters depth, which is the maximum for this current style of spar buoy that we tested, or 150 meters, which is an alternate version that we're currently constructing and testing now. But there's a lot of places, 50, 60 kilometers offshore, where you could put these things. Here's a map of what percentage of your real estate is above a certain depth. Central America is something like 50% of the action is under 150 meters depth. It's a little less in Cascadia, maybe 25%. But this is a potential technique to let us make these measurements offshore. Okay, I'll stop there and give you my conclusions. Slow slip events limit the size of subsequent earthquakes by reducing strain accumulation. It's not clear that they trigger large or great earthquakes. There is this business of correlation versus causality. I think coincidence needs to be considered. There is, I believe, a strong motivation for better monitoring of slow slope events, especially the shallow ones offshore, because they are a key part of the strain accumulation budget and might help us understand the tsunami process. But we need to do better monitoring offshore. There's a lot of action in the shallow parts, and it's an easy target for at least some types of geodesy. Okay, I will stop there and take your questions.